my boy, come on. What's your name?
Siddharth.
Siddharth. Okay, fine. Which class you are studying? Fifth. Okay. I will show you a small demo experiment in physics. You love physics?
Yes.
Very good. What is this? Is a basketball. I hold it like this at a height. And if I release my hand, what happens?
It will go down.
It will go down. It will fall down. And after falling down,
It will come back up.
it will come back. But did you note, it didn't come to the old height? This was the initial height. But when I release it, it comes only to this.
Yes.
Some height it lost. It lost some energy. It lost some velocity. It lost some momentum. Momentum means mass into velocity. Momentum means
Mass into velocity.
mass into velocity. So this has got a momentum. Hold it.
Okay.
Hi. Okay. You know, if this tennis ball is allowed to fall, it comes to a lower height. It loses momentum, mass into velocity. Yeah. So what you are going to do is, your name is Siddharth,
Correct.
right? So you are going to hold the ball like this,
Okay.
and when I say 1, 2, 3, at 3 instant, you must release the ball.
Okay.
Not 1 second earlier, not 1 second later.
Okay.
This is called instantaneous in physics.
Okay.
You got the point?
Okay.
So now, hold it high. No, not you. Not you. 1, 2, 3. Yeah, it was fantastic. So hold it. Now, madam. Yes. Same story for you. Hold it like that. 1, 2, 3. Ah, there is a lot of physics in you. Come on. Now, what you will be doing is, you hold the ball horizontal, and there are lines in it, you see? So we will do one thing. We will find out, there is a hole in it. Can I find the hole? Can you spot me? Ah, yeah, it is. So you hold it like this. And then, madam, you place the ball over it. Now you see what happens. When I say 1, 2, 3, you are simultaneously releasing it. Fine? The ball travels down. The small ball also travels down. Both of them have got mass. Which is the massive one? Basketball or tennis ball?
Basketball.
Basketball. So this will go down, it will have more momentum.
Okay.
Got it? This tennis ball also will follow. This guy will sit on it and travel all the way. Both are free falls. Now, as this ball touches the ground, the fellow will rebound. Now the tennis ball is going down, basketball is going up. This is massive body. It has got more momentum. It has got less momentum. They will hit. There's a head-on collision. Don't be under tension. Relax. Okay?
Okay.
And you know, this some momentum, it will pass on to this tennis ball, and it will lose some momentum. And let us see what happens. For example, Siddharth, this is a truck.
Okay.
I'm traveling in a truck.
Okay.
This is Siddharth motorcycle.
Okay.
You are coming in this direction. My truck comes and hit on you. And now, what will happen to you, you know? You can see. Okay? But then, we have to take some conditions. This has to be vertical, perfectly vertical. This ball has to be perfectly over it. Okay? Then, let us see what happens to the ball. Right? I'm going to say that. Okay. Be smart. 1, 2, 3. Boy! So what happened to the motorbike?
Phew. Bye-bye.
Phew. And where is Siddharth? So, momentum, this had larger momentum, that had lesser momentum. So this is M1, that is M2, beginning. But after collision, some momentum was given to that. So because it got some momentum, its mass cannot change, so its velocity changed a lot. So it jammed away. That is why when you have an accident between a truck and a motorbike is thrown away. Get the point? When the large electric train comes and hits a car, which will be thrown away?
The car.
The car will be thrown away. Isn't it? So this is called total momentum is always conserved. Ladies and gentlemen, this is called conservation of momentum. Momentum before impact equals momentum
After impact.
momentum
After
after impact. Total momentum is always conserved in all collision process in the universe. This law is strictly obeyed. This is called law of conservation of momentum. One way of explaining the law of conservation of momentum is using Newton's second law equation. Force applied ddt of P. P relates to momentum. So if F is 0, P remains constant, which implies law of conservation of momentum for closed systems where forces do not act from outside. The analogous form of Newton's second law in rotational mechanics is tau equals dl by dt. Tau refers to the torque acting on the system and L refers to the angular momentum. So if tau is 0, that is the torque applied is 0, L is conserved. That means angular momentum is conserved in systems on which the external torque is 0. One way to demonstrate this is using a cycle wheel. This is a wheel, typical of a cycle. The cyclist, when he is riding on the cycle, you will see he is balanced. He doesn't fall. But if the cycle slows down and comes to rest, his cycle will fall. So unless it has got a stand, cycles cannot be put to rest. So all cycles have got a stand. Otherwise, we put the cycle there and go away. So under what conditions the cycle holds like this, and under what condition it falls? See, if you look at this typical wheel of a cycle, we recognize this is the axle, and somewhere here will come the center of mass or center of gravity of the whole structure. So the mass of the cycle, mg, will be applying a force downwards. So this force, exactly as I indicate with my finger, the force is directed downwards. And this is the point of support about which it can rotate. So because of the torque R cross F, what is R? R is the distance from this string to the center of gravity. So R cross F will give a torque and the cycle wheel falls down. So, okay. Now if I want to be in equilibrium, I have to apply a force upwards. Now this finger which I am having here holding applies again a torque in the other direction. So that is why the cycle is holding. But when the cyclist is on, when the cyclist is moving in the cycle, I can't grab like that. Now watch. What I am doing is, I am going to rotate the wheel at a fast speed, as if the cyclist is pedaling and he is going. So watch this. Cycle is very fast. Now I remove my hand. Cyclist is not falling. That is, when the external torque is 0, the angular momentum is conserved. What is the angular momentum? When the cycle is rotating, the angular momentum vector acts in this direction, as you can see in the figure. Force I am applying, the torque is R cross F, and this is where the angular momentum comes. So rotating wheels, because I leave my hand free, the torque is 0 and L is conserved. This is a beautiful way of demonstrating how angular momentum conservation is explained with a cycle wheel. One consequence of this is the cycle wheel rotates in the same plane. As you can see, when it rotates fast, it is in the same plane. Now, this explains how the planets around the sun are going in a plane. Now, I can imagine the sun and the earth, a system consisting of the sun and the earth. Let us see. Okay, I will put this place as the sun. Okay, let us assume that somewhere here is the sun. And now I am putting the earth on the orbit. I have magnets here, so I have put it on the orbit. So this is the sun-earth system. And now I can rotate. So the earth goes round and round the sun. But it always keeps the same plane. Why? Because if you look at the picture correctly, the sun and the earth, the distance r is this. The force acts along this line. And the force F and R are in the same direction. R is in this direction, the line along which, and F is also, these are all called central forces. And because of this, R cross F becomes 0. And when R cross F is equal to 0, angular momentum is conserved. So, the plane in which the earth goes round and round the planet is also remaining constant. See, what a great implication law of conservation has got on the movement of heavenly bodies. The same reason for electrons going round and round in the orbits. So basically, conservation law of angular momentum says that when external torque is 0, angular momentum is conserved. We have seen already two conservation laws: conservation of momentum, conservation of angular momentum. The third one which follows is conservation of energy. Total energy of a system always remains constant. This is also one of the fundamental laws of physics. Here I have two balls suspended by strings. They are actually working as pendulums. I have other two pendulums in stock. I can release them, but they are of different length. I have chosen two pendulums of same mass, same length, so that they will have same period. The period of oscillation of a simple pendulum, capital T equals 2 pi into root of L by G. L comes in the equation. G refers to acceleration due to gravity. So since these two pendulums are hanging in Earth's surface, they experience same G. So the period of oscillation depends only on the length. Now I have chosen the lengths as the same. That means the period of oscillation of the two pendulums is the same. So if I allow them to oscillate, they will always oscillate in phase the same time. So I have adjusted the length such that these two pendulums will oscillate in phase. That is, they take the same time. So here are two pendulums of same length, therefore same period, and reciprocal of period is frequency. So these two are two oscillators of same frequency. Now, the energy of an oscillating body like this, any harmonic oscillator, is given by the formula energy 2 pi square m nu square a square. M refers to the mass, nu refers to the frequency, and a refers to the amplitude. So if you have two pendulums which have got same mass and same frequency, the only variable is amplitude. And so I can take in this particular experiment demo E proportional to a square, m and u being constant. So the energy of the oscillator in my case is a function of amplitude only. Otherwise, both the pendulums have got the same properties. Now this means if I oscillate them, the two may differ only in amplitude. So when one oscillates with an amplitude, its energy is proportional to a square, because frequency nu and mass m both are constant. Remember, E is equal to 2 pi square m nu square a square. So the energy of this pendulum, both of them are only amplitude functions. So when it oscillates with an energy, the amplitude is an indication of their energy. If it oscillates with large amplitude, it has got large energy. Small amplitude, small energy. Zero amplitude, no energy. So these are two oscillators, let me say A and P. I am going to pump in energy to A, which means I am going to give an energy to A pendulum, this A. It oscillates with energy, but then you will see this also will start oscillating because they are connected, they are coupled pendulums. There is some way in which the energy can leak through. So if I oscillate this pendulum, this also will pick up oscillations. Let us try that. So I have to oscillate one of them in a plane. That's it. Now watch. This also picks up. This picks up the amplitudes. And now when this has got maximum amplitude, this is virtually stopped. Now this gets energy. It goes to maximum amplitude. And when it is maximum amplitude, this almost stops. And now you see they are handing over the energy to the other one. Now A is oscillating with an energy. Now A gives the baton to B. B picks up oscillations. Now B slows down and then A picks up. What does this mean? If the amplitude is maximum, then it has all the energy. As the amplitude decreases, its energy decreases and this energy increases. So once given an energy, it gives energy to the other system. But E1 plus E2, that is A1 square plus A2 square, is always a constant. This proves the total energy of the system is constant, and once energy is lost by pendulum number A, that will be the energy gained by the pendulum B, and vice versa. This is a beautiful proof for conservation of energy. I now will add one more pendulum to the scenario. Now there are three pendulums. I told you I have got pendulums in stock. Now let me call the names now A, B and C. All the three pendulums have got same mass, same length, and therefore its frequency will be the same. So all of them, when left free oscillations, will have the same energy. But I can control the amplitude. Now A, B, C. I am going to oscillate A and C. Both of them I am going to give them energy. Remember, amplitude is an indication of the energy. Now I am going to oscillate A and C. Remember, B is at rest. B's energy is going to be 0. A and C will have energy. But being coupled, this can also take the energy from A and C. Now let us see what happens. A and C oscillates. Closely watch. B picks up the oscillations and the energy of A and C decreases. But then B starts losing the energy and A and C starts picking up the energy. So total energy always remains constant. This is again a beautiful demonstration. E1 plus E2 is going to be E3. So this is a beautiful explanation of conservation of energy. For a closed system, energy always remains constant. Participants of the system may exchange energy, but total energy remains constant for a closed system. Now, so in the universe, whenever some energy is lost at some place, energy gained at another place, energy lost will be equal to energy gained, and that is a wonderful law behind physics, which is known as the law of conservation of energy. Thank you.